Hello, everybody. Good day. Welcome around the world and those of you watching from the International Space Station. Welcome to hour number 2 of our ECL workshop for Community Day 2022. My name is Bob Foreman, and with me also today is Yugo Watanuki. We are senior software engineers and ECL trainers that are going to present to you hour 2, which is titled Data Delivery with ROXIE, Distilling the Product, Indexing, and Publishing. Now, hour 2 continues where hour 1 left off. If you missed hour 1, go back and watch it quickly. Anyway, hour 2 is based, as all of our workshops are based in this year, on Richard Taylor's brand new book called Definitive HPCC Systems, and his second book in a trilogy, volume 2, Data Transformation and Delivery. Now, yesterday we had focused on chapters 2 and 3, which was getting the data to our cluster, cleaning the data, standardizing the data, and getting it ready for our data delivery today, which is going to be the focus in Richard's book. Chapter 4 focuses on data delivery using ROXIE. And these books, the links for these books are shown below. I would strongly recommend all ECL developers to go grab a copy of this, either on Kindle or either you can even get a paperback copy for your library. So let's get started. In hour 1 of the workshop, we took a large amount of raw data and we cleaned it and standardized it. And the next step in this hour is to turn that data into something that an end user or customer would be willing to pay for. And to make this data valuable to a potential customer, we first must distill the sellable or useful data into information from all that raw data. Only then can we turn it into a product. And just to review, in our ECL IDE, yesterday, this was the data coming in. And you can see that it was all in kind of, well, not shown here, but the results were just a series of numbers, and some of them were like date and time that were combined together. And we work with this into a cleaned or a cleaner format where we now split up the date and time into separate field information. Our passenger count remains the same, trip distance, and so on. But not shown here are the actual record structure of the data that we cleaned, which was, again, converting these variable length strings from our original input into more where fields were numeric, we can convert them into unsigns. Where fields were floating point or decimal, we can convert them into decimal fields, and then the other ones were strings, of course, left them as strings. Okay. So, building our product, our clean raw data, we now know based on our clean data that we have details for each trip, and they are pickup and drop off date and time fields, pickup and drop off locations, distance traveled, fare amount of a trip. And from that information that we've got from our clean data, we can compute new information. Things like which day of the week and which hour the trip started, how long the trip took, the duration from pickup to drop off, and then how far the trip was based on distance. All right. So putting this information together into a data set, we have our pickup and drop off locations, our day of the week, our hour of the day. Now, this is information that's also interesting to the customer. We can also then give the customer the average fare amount and how long the trip took and how far the distance was. Now, to do this, we're going to use, of course, HPCC, ECL, and ROXIE. The information that we're going to be working with will allow us to create a query that can instantly return the answer to the end user question, because all of the answers will have been pre-built and stored in our delivery system, which we're calling it an index. And before I turn this over to Yugo to show you the process, let's talk about what ROXIE is. ROXIE is an acronym that is abbreviated for Rapid Online XML Interface Engine. And unlike Thor, ROXIE is, well, we like to call it concurrent, so that multiple nodes can be ready and working for queries that can be received from the outside world. So all of these nodes have access to our customer. We give the customer access to these nodes through a series of IP addresses. And each node is ready to receive a query. A load balancing system says, okay, either node 1 or node 2 or node 3 will receive the query. Once the query is received, then the particular server of that particular node contacts the agent. The agent on that node then communicates with other agents in ROXIE to determine what data needs to be retrieved. And just like Thor, ROXIE uses a distributed data method. And so the distributed data method, then the server contacts the agent contacts the data channels return the information. The beautiful thing about this, a couple of things to say about this, is number one, all of the queries that are stored on ROXIE are pre-compiled, so they're ready to run. Also, the data that is stored on ROXIE are indexed data sets. ROXIE is built for high throughput, millions of users receiving sub-second responses. A typical production cluster in LexisNexis can return up to, well, I used to say 12,000 queries per second, but the hardware guys in my location tell me that I'm being very conservative. And there's built-in redundancy. Copies of data are stored on 2 or more nodes. Any peer, any node can deliver a task for a channel, and there's high availability. All right, that's a quick, very quick overview of ROXIE. In our online lessons and in our classes, we go into ROXIE in much more detail. But I just wanted to give you a high-level overview of ROXIE, and what we're going to be doing with our ECL now is building these index data sets into a pre-compiled query that eventually we're going to show you and we're going to publish. So without further ado, I'm going to now turn it over to my colleague Hugo, who will now talk to you about the process of our clean data and moving it into a product for our customer. Hugo, take it away.
All right, thank you, Bob, for the very nice conceptual introduction on ROXIE and our product need as well. So now I will take us through the code development of our product, right? And to start with, we'll first need a way to calculate the duration of the trip from the pickup date and time and drop-off date and time, okay? First, we'll need some constant values to do this calculation. And this is the kind of standard code that belongs in the util folder of our code repository, okay? So let's just start with the first ECL file here, secs.ecl. This ECL file contains basically some integer constants. These constant values are the number of seconds in a minute, the number of seconds in an hour, and the number of seconds in a day. And we can use the enum function to define all three in a single line of code and reference them using standard dot notation, right? And enum function removes the requirement of magic numbers or hard-coded values, for instance, 60 seconds or 3,600 seconds contained within an hour. So those hard-coded values will not be required in our code. And that improves code readability and maintainability as well, okay? The second utility function we will require here is the trip duration calculator, which we call TripTime.ecl. Since we will need to do this calculation for every record in our input data set, it makes sense to create another utility function just to do the work. So we'll put this code in the util folder of our code repository as well. But the TripTime ECL code, as I will show you next, is basically a function that contains a nested local function to calculate the total seconds in a time element. And why we are so concerned about calculating the amount of time in seconds? Basically, because we want to take into account the possibility of a tax trip being made between, you know, a very late hour in a day, like 11:45 p.m., and the drop off being at very early the next day, like 1 a.m. So the trip days definition uses the standard days between function to determine days spent in trips, and that will help us with that calculation, okay? And of course, if the trip is contained within the same day, we'll rely on multiplication by 0, and the return expression will work either for single or multi-day trips, no matter what's the input parameter, okay? So let me tab over to the ECL IDE, and we can take a quick look at those code examples. So first, the enum function, nothing much to say there, but the trip time is a little bit more interesting. So trip time, as I mentioned, is a function structure that receives pickup and drop off date and times, right? And it calculates the total number of seconds elapsed between pickup and drop off. Okay. Now, inside that function, I have a nested local function just to convert the numeric values from the time information into a string format, a 6-character string format. And then I'm indexing each pair of characters from that string, that 6-character string, into their respective sections of hours, minutes, and seconds. And of course, multiplying that by the definitions or the elements from the enum function we have seen before. And then I'm just concatenating all the values or all the amounts in seconds, okay? The last piece of this function is basically leveraging this nested local function above and converting the drop-off and the pickup time into seconds, and also considering how many days have passed between the pickup and the drop-off date. And then, last but not least, I'm just summing up the drop-off amount of seconds, taking into consideration the amount of days between drop-off and pickup, and subtracting from the pickup amount of seconds, okay? Since my baseline is 0 hours and 0 minutes of every day, right? Now, we have then all the utility we need, so we can move forward and start thinking about distilling our product, okay? Now, to support the functions we are going to need, the next step is actually to extract the information we want from that cleaned and standardized data that Bob has just displayed at the beginning of this workshop. So we'll use basically table to extract the fields that we want to work with, and also a lookup function to format the elapsed trip time output, okay? Remember, we are also interested in extracting the average amount of the fare, the duration of the trip. So we'll use a crosstab functionality to do that, okay? And all that logic will be contained within the prod data.ecl code. So let's tab over to the ECL IDE. Okay. All right, so prod data.ecl, as you can see here, contains some local definitions, one local function, and actually the exported definition right here. The first local definition, as I mentioned before, is basically a vertical slice. So we are picking up the original text data file and just selecting the fields that we want to work going forward. So rec ID, trip distance, pickup location ID, drop-off location ID, for amount, the hour of the pickup and the day of the week. And right here, as the last field, we are leveraging the utility trip time function to calculate the amount of seconds the trip has actually taken. All right. Now, since we are working with a total amount of seconds, you might want to display that information into a more visual aspect, if you will, like in hour, minute, and seconds as a string result. So that's why we have this local function here, just picking up some unsigned 8 value and using the informat function to convert the amount of seconds into their respective values for hour, minutes, and seconds. And then this local function is basically concatenating those strings into the hour, minute, and second format that we want. Okay. And then finally, to really distill our product, we are doing a cross tab here, filtering the vertical slice for any trips that are different than 0 in terms of distance and duration, right? We just want meaningful trips into the product. And apart from the 4 fields that will be used as filter parameters in our product, we are doing a cross tab to extract the average values for distance, fare, and duration for each of those trips. So all this data will be calculated in order to be displayed in our final product. Okay, I'm using a persist here just so we avoid doing this cross tab every time we call the prod data definition. All right. Now, if you want to see how the data looks like at this point in time, we do have this BWR file here that you can execute. So the first output here is the prod data. As you can see, this is how the data looks like right now. So instead of having all the fields from the original data set, I just have pickup location ID, drop off location ID, day of the week, hour of the day for the pickup, the unique groups that I have within those fields, but I guess more importantly at this point in time, the average values that we just calculated. Okay. All right, so it's time for us to tab over to our slide presentation because now we have the data distilled in the format that we want. But there is a next step or a very important step that Bob has already highlighted in his previous introduction, which deals with indexing the data. Okay, so ROXIE queries are almost always actually defined to gather data from index files, because that's the fastest possible access to individual items in the data. So next in our process is to create an index for our end user query to use. Okay? But bear in mind, recreating the production index as new updated data comes in will be a standard process going forward. Okay, so we need to create definitions that we can use repeatedly. And building the index, we also generate the record structure that we need for the index that we will define next. Okay, and the indexing is done with the assistance of this ECL code here, prod idx.ecl. So let's tab over to the ECL IDE once again and see how that code looks like. Sharing here on my screen. And you can see that the prod IDX is actually a module structure where we have grouped all the exported definitions that we want to work with. But let's start with the initial piece here. Let's focus just on this section of the code. Here I'm defining the index logical file name. It looks familiar. It should look familiar for you right now because it's basically the same syntax or the same format that we have used for naming our logical files. The different piece here is that the fact we are using a build action to build the index. Okay, so whenever I need to build an index, I need to provide the original record set from where the index is being built. And I'm also providing within curly braces here the fields that will be indexed. Okay, these are usually the fields that will be queried by my final product or my service. Okay. As a third parameter here, I'm passing all the remaining fields from the original record set. Those will be payload fields. the index file name, and I'm just overriding this or passing the override flag here just in case I need to review this index from time to time. Okay. Now, remember, defining something does not trigger anything per se on the cluster side. So you actually need to have a BWR to build your index. And that's what we have on our support BWR right here. So you can just comment the output we were seeing before, and you can call the build IDX definition to actually build your index. Once you do that, you won't notice too much difference from the previous data set, apart from the internal file position field here that has been displayed. But your data is now indexed, and you do have the support of a binary tree to help you locate the fields that are matching your search criteria. Okay. Very well. Now, moving over to the next slide, we do have our index created, right? But remember, before we use any data structure on HPCC systems, there is a very important step that we need to take, which is defining the index, just like we define a data set. So once that work unit that built the index is completed, you can basically go into the ECL Watch and search for that work unit. And on the output tab, you can click on the result file name to open the logical file details, just like I'm showing on the screen here. And if you click on the ECL tab, ta-da, you will have the record structure for that index you just created. And you can copy that record structure and paste it into your ECL code so you can define the index completely, okay? So finally, defining the index, once created, you must look at the record structure and modify your product IDX ECL file, okay? And you can do that by just pasting the record structure from the ECL Watch page I just displayed. That, believe me, that will save you not just typing effort, but ensure that you don't fumble finger the typing, you know? And you just need to modify the prod IDX ECL file once again, but now to add a super file as well. And I will mention in a few seconds why we need the super file as well. So here is basically how we add the super file into that very same ECL file. So let's look at that ECL file just to make sure we comprehend what's going on here. So prod IDX, and here you have the record structure we just pasted from the ECL Watch page. Here is the index definition. So again, this index file name is already something available on the cluster. We just built it. And I'm just defining the index using this record structure and that index file name. And as I briefly mentioned on the previous slide, we are also defining a super file or super key here, if you will, with the very same record structure, but now with a different logical file name that I'm specifying here at the top. Okay. You can output the index, you can output the super file, the result will be the same. You won't see too much difference on that aspect, but remember, just like we did in our one, you actually need to create a super file. Just defining it won't make anything different on your side. So let's move over to the next slide that will show us how we can create the super file. Okay, so just select the index that we just created. Remember, you were almost there looking at the record structure, and click on the Add to Super File button. And once you do that, you can name your super file as DG text IDXSF and just click on the Add button. Right? So that will create the super file for you as the sole subfile being the index we just created. Okay. So I know at this point in time, you might be questioning why do I need a super file? So just to clarify things a little bit, ROXIE queries need to always have up-to-date data, right? So the index will need to be reviewed every time you have new data. We've already briefly mentioned that. Now, you don't want to have to recompile the query every time you update data, because really complex queries can take 1 hour or so just to compile. And I mean, you don't want to unpublish and then republish the query just to update the data, because that will cause you service interruption, right? Business interruption. So the easy way for you to not recompile a query every time you need to update the data is to use a super file, because you can use the super file just like an alias for whatever subfile it happens to contain, right? That's the logic of a super file. And the trick to updating the data actually lies in the concept of package maps that are very nicely discussed in this blog by Dan Kemper that I'm listing on my screen. But basically, looking at the package map process is a three-stage process. You build the index, you copy the new index to your ROXIE, and then you update the ROXIE package map just to change the subfile name. So doing like that, you are just dealing with DFU metadata, and your ROXIE query will be instantly using the new data as soon as that has been done. Okay. All right, so we have taken care of all the data needs for our final product, except for one minor detail. Not sure if you guys recall, I can perhaps bring up the ECL ID once more, but if you look at how our index data looks like, it's still using numeric values for pickup location ID and drop-off location ID. So that's okay for you to use in the internal logic of your code, but you might agree with me, those are not very user-friendly in case you're interested in using this product. You might be interested in actually seeing what's the location name for pickup and drop off. So that's why before we build the final query or the final product, I took some time to follow the steps from the author of the book and build a zone lookup file, okay? So to help me with that task, and you can do the same on your end, you can download the CSV file containing all the location IDs from the areas of New York City from where this data set has been pulled. And this is the URL from where you can get that CSV file. Once you have the CSV file, you can basically download it and spray it to the cluster. And then you can duplicate the code that I will show you in a few seconds to obtain a record set, just like I'm sharing on my screen right now, okay? So here I'm associating each location ID to its respective borough, zone, and service zone. Okay, so that's the information I want to display on my service instead of the location ID itself, right? So let's look at the zone lookup table. Let me switch over to the ECL IDE, and this is the code for the zone lookup. Nothing very special here to begin with. We just have a module structure, the record structure for that CSV file for fields, and the dataset declaration for the logical file that has been sprayed. Now, the interesting bit here is actually the dictionary definition, the DST definition. Normally, you might expect to define an index to handle the lookup of a specific location ID values and return the zone values. But since this CSV file is only 100 records long, I would expect that information also to almost never change, because they are basically areas from the New York City. So in that case, using a dictionary actually is the better solution, okay? A dictionary can be defined from an existing data set, just like we are doing here. And it will act like a payload index, okay? So it gets the data set, the dictionary definition, gets its data from the file, and it's indexing it to the unique values of the location ID field and payloading the corresponding zone field, all right? Now, you can use, for instance, a function like this, ID to zone, where you now pass the location ID, and the location ID will be retrieved from the dictionary, returning the zone string name corresponding to that ID. Okay, so that's the special piece of this code, in my opinion. And to conclude this lookup table, you might be interested in looking at what's the shape of that data set now. Nothing very special here, just the location ID, the borrow, the zone, and the service zone. Okay, so that's the information we will return for anyone using this query. Okay. Finally, we have all the pieces together, and we can now dedicate some time to build our ROXIE query. Okay. We will call the product here text data service, basically because ROXIE queries are data retrieval services. You can think like that. So it's typical to name the query as a service. This service takes as parameters the 4 search items or terms in our index. Remember, pickup and drop off location IDs, day of the week for the pickup, and hour of the day for the pickup, right? Optionally, we will use the started workflow service to replace those parameters. We will also provide default values of 99 for any parameters that you might want to omit in case that's desired. And all the filtering logic will be contained within a map function. So depending on how many parameters are being passed, we can filter the index accordingly. And one specific item that I will briefly mention here, we will use keyed and wild just to make sure our index is always filtered using the binary tree and not using a full table scan, okay? And last but not least, the results of the search will be formatted to provide proper translations of numeric codes to more readable information, all right? So let's look at the text data service.ecl file. Let me tab over to the ECL IDE. And that's the most important piece of our code, I believe. Let's take a look into more details here. So we start this query by defining or redefining the index that will be used in the query. Remember, we just have one index. That index is now part of a super file or super key. So that's what we are specifying here at the top of the code. And then everything else is basically contained within a function structure that receives pickup, drop-off ID locations, and day of the week and hour of the day. Okay. Here we have 2 Boolean conditions being checked just to make sure or to compare whether or not the function has been provided with input values for day of the week and hour of the day. 99 are pretty far values from what a regular user would pass on these parameters, okay? And depending on that condition, we are using this map function here to do the proper filtering. So if the user did not pass day of the week and hour of the day, just filter the index based on the location IDs. If it's passing no hour, do the appropriate filtering. And if it's passing no day, the appropriate filtering. Now, the no day is a special case because once the user did not pass the day of the week, that means you will be filtering the index by a trailing field, okay? And whenever that happens, you might need to tell the compiler you are actually willing to do that, and while deleting field, so so the compiler will not try to do a full table scan here, and it will actually scan the binary tree, and that will make the filtering faster for you. Okay. That's the core logic, filtering so we can get the desired result. But just like I told you before, the result of the filtering might not be on the format you are willing to make available to your final user or to your final customer. So that's why the last piece of the function is dedicated to formatting the query results into some more human readable strings. Okay. So we are doing that basically with a project transform. So I'm passing here as an input for the project all my filtered indexes, and then I'm transforming them record by record. So this is the final format of the project. I'm displaying the pickup, the drop-off, day and hour of the pickup, duration of the trip, average fare, and average distance. And even though duration, fare, and distance are not being transformed because they are basically numeric values, I am transforming the pickup location ID from a number, passing it to that ID to zone function we just saw in the zone lookup, and then I'm returning the actual pickup location in string format. The same logic is applied to the drop-off field, and then day and hour are being transformed by these two local functions here defined at the top of the code. And those two functions are basically receiving the numeric value for the day of the week and the hour of the day, and use the choose function to accordingly return what is the corresponding string for day of the week and hour of the day. All right. That's the function that we want to create. That's the function that will support our service. You can now test it if you will. So if we go back to our PWR, you can comment now this zone lookup file, uncomment these 4 output actions. And you can see here we are passing 4 different set of parameters for that function. I'm passing pickup and drop-off location IDs, day of the week, skipping day of the week, and passing hour of the day, and finally passing all the 4 parameters. So if you submit this code, you will end up getting 4 results. First, just filtering the data set or the index by pickup and drop off. I'm receiving here all the days of the week, all the hours of the day. And here is the interesting information: duration, fare, and distance for each trip. If I become being more specific on my query, I'm now passing the day of the week. These are the results for each hour of the day. If I just pass the hour of the day, it will return me all the days of the week contained in the index. And finally, if I'm fully specific, I would mean in my query call, I will just get whatever average fare, distance, and duration is contained for that specific hour of the day of the week, and pickup and drop-off locations. All right. So that's how our product looks like at this point in time. Good. Now you might be thinking, okay, we created a ROXIE query, but we ended up with just a standard function that pretty much looks like any other. So how do we make it a ROXIE query? Okay. So this is something I will demonstrate in the next couple of slides, as it involves publishing this code, pre-compiling it. And the first step here is to make sure I can allow the final user to specify these input parameters during execution time. Remember, the queries are pre-compiled. So I can do that by uncommenting this section of the code here. I'm just eliminating all the input parameters from the function definition, but I'm specifying here the 4 input parameters using the stored workflow service. So the stored workflow service is actually the feature that will allow the user to provide the input parameter during the execution of the query, even though it's already precompiled. Okay, so by doing this change, you have your code ready to be published. And how does publishing work? First of all, make sure you change your target to ROXIE. That's the first time we're doing this. Remember, so far, all the heavy, dirty work has been done in Thor. And you just need to compile this code. So just click on compile, and you will see that your work unit now has this green circle showing that the query has been compiled. Once that is done, just click on the ECL Watch tab and publish your query. Yeah, you can change the job name if you will, or just go with the standard name. And once you click submit, ta-da, your query is now published. A lot of things happen in the background. You have pre-compiled your code. Your pre-compiled code has been copied over to the ROXIE cluster along with all dependencies. But most importantly, you might be interested in testing that query. So now that we have the pre-compiled query available and our service is somewhat ready for testing, you can use a web service that comes by default in every HPCC Systems installation, call it WS-ECL. So this service is always available by default on your HPCC Systems cluster. The port number is usually 802. It can be slightly different depending on how your systems administrators wanted to set up that. But once you have access to that WS-ECL service, you basically need to look at the target where you published your query, and you will see that now you have end user interface that allows you to provide input parameters without the need of the ECL IDE or without the need of any ECL code actually. Okay, so let's pass here as a test the same elements or the same input parameters from our previous test and click submit, and there you go. You have here this very same result: pickup and drop off locations, day of the week, hour of the day, and the average values for duration, fare, and distance, right? At that hour of the day, on that very specific day, short trips is the average value. All right. So from this point onwards, actually, the sky is pretty much the limit, right? This is an interface for you to test your query, but you can use the links tab here and use these endpoints to actually build something externally, like a web portal, and call this service using the the endpoints listed here. Of course, you can also build your own web service for production usage, which is the recommended approach, by the way. All right. Very well. So let's wrap up here. We are almost done with our product, but just to recap what we did. So before publishing, we can test the query result in Thor. I just showed you how to do that. The steps to publish are really simple. You just need to set your target to ROXIE, compile only, and then publish from ECL Watch. You can also test your query via the WS-ECL service, or actually from the ECL Watch published queries interface as well. But remember, this is a programmer's testing tool. So if you want to have something more tailored to production usage, you might want to come up with your own web service. Okay. All right, so this concludes this part of the presentation. As you have seen, we have basically taken the data from our one workshop, sliced the content that is meaningful to our product, shaped the data into a format that can be queried and it's visually appealing to the end user. And finally, opened an interface that can be used by basically everyone that would like to consume this service. This is the basic of working with ROXIE, but in case you need some unconventional or more advanced technique, the author of the book also demonstrates how you can work with descending indexes and bitmap indexes. And this is actually something that my colleague Bob Foreman will demonstrate in the next couple of slides, okay? So if you're ready, over to you, Bob.
Thank you very much, Hugo. That was an excellent presentation. Well done, well presented. And you know, this book is packed with all kinds of gems. I've been working with ECL for over 11 years, and I started reading Richard Taylor's book, and I started looking at some things, and I went like, oh, I didn't think I could do that. And, you know, sure enough. So there are things for the beginner in this book. There are things for intermediate level. There are things for advanced users. And the last couple of slides I'm going to show you are just some of the other tips that Richard talks about. This is in his section called the cookbook chapter that Hugo and I are going to, well, we're making a valiant effort to cover as much as we can in the third hour of our workshop. But, you know, as it goes, we're not going to be able to cover everything. And so we decided to move a couple of the tips in the cookbook into this section here because these do focus on indexes and data delivery. So there's 3 ECL files I'm going to show you in just a minute. GenDS, which generates our test data, a bitflip string ECL file, which bitflip str, which I'll explain what that's doing. Actually, just taking a string and flipping the bits around. And then the last one, building the descending index. I actually took liberties from the author. The author called it descending index.ecl. I wanted to just, since it's a runnable file, I just renamed my file for this workshop. Now the code's going to demonstrate using date functions to do date arithmetic. I think we've already shown that already. Generating random birth dates and names, that's in that GenDS module. Using negative integer values to create a faux descending integer index search term. This is something I learned that I didn't realize that the technique behind this to do descending numeric indexes, and also, well, stand by, create a function to flip all the bits in the string, because we're going to also create a faux descending string index. All right. So we're also going to show, once you've created these indexes, well, how do you work with them? How do you filter them with specific records, ranges of records, and specific sets of records? So over back to my ECL IDE. This is the code behind GenDS. You can see that Richard has set up a records to generate 10,000. So if you needed more to test, you could change that counter from if needed. Here's his function that is working with some sample dates. He's got a record ID, a birth date, and a name. Very simple test data set to demonstrate his descending indexes. He's got a simple transform here that he's working with a generated data set and an output. So this is all encapsulated, again, inside of a module. So in order to actually run this, like I said, I'm going to show you it in our build descending index. The other function that he brings to focus in this chapter is one where he's taking a string and doing bit flips. All right. And I have to say, I'm not a guy that does bit flipping every day. So once again, you know, in our introduction to ECL class, we've got just a kind of a shortcut here. If you're doing bitwise ANDing or ORing or exclusive ORing, these are the operators that you use when you're doing bit manipulation, or what he calls, I think, well, The author also has a very interesting blog, which I will share the URL to that blog in our chat, where he talks about, I think it's called bit fiddling or bit twiddling. I don't remember that it was fiddling or twiddling, but you get the idea. He takes these bits and he moves them around, and he's doing all kinds of stuff for working with dates. So this is his function here, where he's flipping a string that gets passed through this function and returns the flip value of that function. And there's a lot of code explanation behind this, just not enough time to talk about it. But trust me, it works. Putting it together. Now let's talk about our descending indexes. So I've got several outputs here. Output of, well, first of all, the general output of this gen data set. That's the first step right here. So I uncommented that because I already generated it, but we have here a sequential operation to first generate the data set, then build a descending index of an integer, I descending index, and then building a string descending index. Step two, he's just the author is picking a single record from his generated data set, and then showing you, first of all, how to extract it. And by the way, there's an interesting explanation here on why in line number 8, he was using this type of syntax to generate a single record, of course, from 42 to 42. He goes into an explanation that using just to retrieve just a single record, using just a single value in here was returning errors because it wasn't really returning a record. This reference right here is returning a record set. So we call that one record. Then he demonstrates how to process the actual, by doing a flip of the negative date, it becomes a positive date. So when we're trying to look for a positive birth date, even though we're in a descending format, taking a negative of a negative is actually resulting into a positive. And then he goes again, does a negative of the negative date to do ranges between 2010 and today's date. For the descending string index, he does his bit flip string of the record that's getting passed in, does the filter on that accordingly, and then also demonstrates the ranging between the last name of Miller and the last name of Jones. All right, so you can see here, here's the single record that we chose to test, which was Doria Bird or Bud, or anyway, so these are fake names. And there was the filter on the descending index, grabbing the single record, the range using the descending index, of course. And then once again, one record for the string. And there's that reverse name, that bit flip that the author does, gives you that, well, it doesn't give you an ASCII result because these flip bits are going to give you non-ASCII characters. So it looks kind of crazy, but it works. All right. And here is the string in descending range. So in the range of last names, you've got Miller all the way down. And because we're using output with the all, we can see all the records, not just the first 100 from the IDE. So in that range between Miller and the J last name, Jorans is the last name before we get to the range we were looking for. Sample, this was the sample records of just taking a sample and filtering on sample result. And then that's our, and then here's the descending of those sample records. So we have Zester at the top and Akjar at the bottom. So the descending is working beautifully. All right, and there's one more example that, like I said, we're out of time here, but I'm going to encourage you to look at this. This is, first of all, Richard has also provided in his book a series of utilities, and there's a folder that he stores all of these utility functions in. So he's got some special functions like bits, which I'll explain in just a minute. And also he's got another function called bit, which has got all different ways of working with a with different bits. So for example, return a single bit pattern, sets or returns a single bit, test the single bit, and then test the bit pattern for all past bits on. So, and then at the bottom of his example, he's got ways of testing these individual functions that he's written inside of this module. All right. And so finally, he's got an example here called bitmap index, which I thought was brilliant. Again, kudos to the author. This was really cool stuff. And he's talking about, well, what happens? And he actually got this idea from a user that emailed him, and he said, oh, you know what? Let's dive into this and let's get this done. So he has a bitmap here that he creates. Let me just show you what that looks like. There it is. He's got his gen data, and he's added an additional field here called bits. And now he's going to enumerate into that bits field to determine, okay, do I have surfers or skiers, or let's see, where was that? That was in here somewhere. All right. That was in the, oh, here it is, right here. Sorry about that. Just had a, just lost my way there for a minute there. There's the enum. So he says a sport. Let's take the bit pattern that he's got generated. And if it has the first bit turned on, he's a surfer. If it's the next bit turned on, he's a runner, etc. So then by using his suite of functions, he does bit mapping together, combining surfers and scuba divers and sailors, calling them SDS scuba divers and sailors. And then he's got another bit map here of surfers and sailors. Down at the bottom, he then joins them together with some very clever code, producing an output of all the people that match between those bitmap results. And also, to be a little more exclusive, he also puts in his join condition a filter by name. So just marvelous stuff. And just to wrap this up, I'll take you over to the ECL Watch, and we'll take a look at the surfers and sailors. And you can see with his indexing that he's built, adding that bitmap to the index, using his bitmap functions to process the individual results there. He's now doing a match between names of scuba divers, and sailors to the other result, which was surfers and sailors. All right. Now that's just a taste. I'm really just teasing you with this because there's so much information in this part of this book that you need to dive into, you need to get, you need to pour into, and it's just marvelous. It's just a great reference material. That's why we're excited about this 3-hour workshop. Maybe we should have made it a 6-hour workshop. I don't know, Hugo, but anyway, that's it for data delivery, everyone. So I want to thank you for attending hour 2. I do want to mention that, you know, we'll be around here for the remainder of the time. If you still want to drop questions into the chat, please do that. And also during the course of our workshops, I should probably mention that in the beginning of it. You can also type in questions in the chat. So thank you so much for attending. We've got a whopper of a workshop in hour 3 coming up. We're going to go into the ECL kitchen, and we're going to open up Richard Taylor's ECL cookbook. So for behalf of myself and Hugo, thanks everybody. Have a great rest of your day, and we'll see you tomorrow for hour number 3.